explain he moved to Lakewood 18 years ago. He's actually been very active with the Flatirons Mineral Club in Boulder. And you are a past president of that club,
yes,
aren't
I
you? Among other things. And Dennis is also very interested in fossils, and I think that's his real main love. And when you see exhibits from him at the Denver show, it's usually a fossil.
And our show too.
And our show too.
Yeah.
And Dennis is I don't know the details of his background, but he's a mining engineer, or has been a mining engineer.
Oh, no. I'm a chemical engineer.
Chemical engineer.
And so you're going to learn chemistry tonight. I'm going to force it on you, so I hope you enjoy chemistry tonight.
And it says that he has worked with lithium in the past before it became the rage. And I'm sure he'll tell us some about that. So Dennis, thank you for coming and speaking. And do you have a place you can...
Have them raise their
Okay,
hand.
good. Anyway, yes, as Pete said here, well, a little bit of background here. I went to school at the Colorado School of Mines. I'm not a geologist, I'm not a mining engineer, but I'm a chemical engineer. But for most of my career, I worked for a company called Hazen Research, which is only about 15 minutes away from here. And Hazen works with mining companies and other companies to develop processes to recover metals and other products from rocks and other materials and stuff. And so I wore the t-shirt here, and I worked on most of those metals there, and I did a lot of work on lithium. Although I've been retired for, I guess, 5 years now, Hazen was doing a lot of lithium work even 10 years ago because it was becoming very obvious to people that lithium was what I call one of the metals du jour, and along with rare earths and cobalt and copper and others too. So anyway, so I'm going to talk about lithium. This is kind of informal, so if you have a question, you don't have to wait to the end. Raise your hand and speak up, and if I remember, I'll repeat the question so the Zoom people can hear it, and we can talk about that. So like I said, this is pretty informal, and we will get started. So anyway, really, it's kind of have two parts. One is where does lithium come from? And the other part, I'm going to talk about lithium batteries a little bit, because that's obviously what's driving the huge spike in demand in lithium. So where does lithium come from? This shows you where it is. So anybody have any questions? Okay, we'll go into a little more detail. Okay, so lithium. Lithium, I told you you're going to get chemistry. Lithium is right here on the periodic table, and that's very, very important. The periodic table is, if you don't remember high school chemistry and such, it really does tell you a lot about the various elements and the properties and such. So the fact that it's the third element here, that tells you it's very light. And obviously, that is one of the big draws of using lithium in batteries and such. Its density is only 0.53, about almost half as heavy as water. So it's a very, very, very light metal. It is alkali metal. The alkali metals are this column right here. And the alkali metals, they have anything that's in a column like this tends to have similar chemical properties. And so lithium is here with sodium, potassium, and then there's rubidium, cesium. Those are less common, but also very important economically. And so the property of lithium is going to be very similar to sodium, potassium. And what that tells you right away is, gee, if I have to separate lithium from sodium and potassium, it's going to be very difficult because they have very similar properties. And to do separations, I have to find a property that makes lithium different from the other things that I want to get rid of, but I don't want anymore. So an important thing to keep in mind. And it is the most reactive metal. And I'm going to try to show a video here to show you. So give me a second here. Okay, so before I show this, how many of you people are carrying a cell phone in your pocket? Okay, that has a lithium battery in it, of course, because that's what powers them. Okay, I want you to watch this video here, and so you can think about it a little bit here. Oh, we have no sound in this, do we?
We can read.
Okay, well, you can read it and watch it. I wouldn't recommend doing this, by the way.
Yeah, don't do this. Leave them long enough, they'll do that for you.
And you can see lithium looks just like a metal. I mean, it's soft. You can see how easy it bends. You also notice he's wearing gloves. Good idea. I would recommend doing this.
Nice!
Okay, so I want you to think about this video here when you have that cell phone in your pocket. Okay, so let's talk about lithium. Everybody knows that lithium is in high demand here, and you can see here's kind of worldwide production, and it's running along at about 30,000 metric tons a year up until about 2017. All of a sudden, it starts going up and up and up. The last year that there's numbers, which was 2021, it's about 100,000 metric tons of lithium is produced in the world. And we can all probably guess why that demand has climbed up there. And this shows just what you might think. So in 2010, batteries were about 23% of lithium. There was actually more lithium used in ceramics and glass at that time. And other things, the lithium greases, some of you may be familiar with those. And there's some other minor things here too. Well, in just 10 years, batteries went from 23% to 71% of lithium use. The rest of these uses, the amount of tons is about the same. That hasn't really changed all that much. But so the growth is really in batteries. And for instance, electric car has about 73 pounds of lithium in it, in those batteries. And so, the more electric cars we have, and the electric cars are driving it, the more lithium we're going to need. So, where does the lithium come from? As I say, lithium production about 100,000 metric tons. A metric ton is like 1.1 U.S. tons. I mean, so they're about the same, approximately. So, okay. So, where's it coming from? Australia is the largest producer in the world, producing a little bit over half the lithium in the world is coming from Australia. China is number 2, or I'm sorry, Chile is number 2, and we'll talk about why Chile is such an important producer. You can see the United States is way down at number 5. There's only one producer of lithium right now, and so the number is approximately 500 metric tons. We don't exactly know why, because that's proprietary information. They don't release that, but you can get kind of an idea on that one. So, one estimate is by 2030, so another 10 years, we have to produce 4 times as much. One of the things that has come out here is both California and New York have mandated that all vehicles sold by 2035 have to have 0 emissions. They have to be electric. And there's new things that have just come out here we'll talk about a little bit later. So that shows us where we're coming. However, there's supplies. And question, yes, go ahead.
So is virtually all of Australia's lithium going to China?
Just about all of it, yes. The question was, is all of Australia's lithium going to China? Pretty much there. Most of the lithium is owned by Chinese companies, and it's going to China. And this is one of the reasons why you can see right here. As I say, China only produces 26%, but the concern with China is they control almost 60% of the world's capacity of raw materials. Again, mostly from Australia, just like you said, and but also they're also in South America. Even more disturbing here is 90% of the batteries are made in China, and so this is one of the things that's driving the concern of the U.S. government with strategic metals, lithium being one of them. Now, will the government do anything about that? Well, we'll see. Okay, so really there are 2 sources. That first screen kind of showed you there are 2 sources. Just a little over half of the lithium comes from brines. So these brines are mostly in Argentina and Chile and Bolivia here in the Atacama Desert. and we'll talk about those some more. The rest of it comes from hard rock mining, pegmatites, mostly from spodumene, and there's a couple other minor lithium minerals that provide lithium here. There are a few other sources. One is hectorite clays. This is getting all the press right now because Tesla has invested in this mine in Nevada. The sources of lithium are these hectorite clays, and we'll talk about some of the challenges with that one too. There's another mineral called jadarite. It comes from Serbia, and it's kind of an interesting mineral, but it's a lithium-bearing mineral, but also has boron in it, so you can get two products out of that, which is kind of an interesting thing. People have looked at geothermal brines, particularly in California, that have some lithium in it. Some of the petroleum production brines also have lithium in it, and we'll talk a little bit about challenges from all of these. None of these are commercial at this point, and we'll talk about why here in a little bit. Okay, so the first is lithium from brine. It's the biggest source. It comes in the Atacama Desert. There are these dry lake beds. They're called salars, and just under the surface here is brine, and the brine has lithium in it, ranging from concentrations from maybe averaging 600 to 1,000 part per million. I mean, so it's not a lot of lithium when you consider all the other stuff that's in that brine, but it is quite commercially viable here. And so here's kind of a process, a generalized process of how they get lithium out of these brines. So we'll start out here. They drill down in the salars, they pump out the brine, and they put them in these big evaporation ponds. And these ponds look like this. And there are these big square ponds here, and these squares are probably, maybe 500 to 1,000 feet long, and maybe a third as wide, and they are generally they dig them down in the salar. I mean, this is just like salt essentially, and they will pack it full of clay that's impermeable to water, so they can seal it, so they don't want to lose all the brine. And they just sit them out here in the sun. The Atacama Desert, it rains once every 100 years, so they don't have to worry about their brines being diluted with rain. And they just let the sun evaporate the water, and so quite energy efficient. And as the brine evaporates, as you can see here, as the brine evaporates, the first thing that will start crystallizing out is halite, salt. So sodium chloride comes out, and the sodium chloride is really a waste. There's not a market for it. They're in the middle of nowhere. You know, the Atacama Desert's like at, 10,000 feet, and not near any kind of civilization, so the salt is worthless. So essentially they just pile that up. In fact, I think here's a picture of it. What they do is they'll let it evaporate out, pump the brine off, let it dry out, then just take front end loaders and they bulldoze it up like this and they haul it away. You can see how big these ponds are. I mean, these ponds are huge. Let me back up here. We'll back up to this one. Then as more water evaporates away, other minerals crystallize out. The next thing that comes out is the sylvanite, the potassium chloride, and they harvest those salts. Again, what they'll do is once it's evaporated down far enough, they'll pump the brine off. They let the pond evaporate to dryness, then they take front end loaders and they'll load this up. And they'll take this to the potassium operation and they'll produce potassium chloride. Potassium chloride is used as fertilizer, and that's a marketable product that comes out of here. Further evaporation, you start getting these mixed salts, and you get potassium sulfate. You get also magnesium sulfate, magnesium chloride. More magnesium chloride, actually, magnesium sulfate, also precipitate out, and then that goes also to another processing operation to make potassium sulfate, again for fertilizer, for potassium source for fertilizer. And then at this point, your brine is quite concentrated. We started here, as I say, that's 300 to 600 part per million, or 0.03 to 0.06% lithium. We're down here, it's concentrated to 4 to 6% lithium. So we have evaporated off 99% of the water has been evaporated off to get that concentration. and all done with the sun. Another thing that's very important is the magnesium to lithium ratio. We'll talk about why that's important. It starts out at about 22 to 1. By the time we get down here, it's 1 to 1. And again, the magnesiums come out here, and to be economically viable, these brines have to have a low enough magnesium concentration. And we'll talk about why that's important here in a minute. So we talked about those. You know, here are the plants here that are, say, recovering the potassium salts here. And also we'll do more of the downstream processing in those plants. Again, you can see there's just nothing out there but flat salts, dry salt lake. And so I said magnesium is an issue, and the reason is to get rid of magnesium out of there, you have to make magnesium hydroxide, and they do that by adding lime to it, and it precipitates magnesium hydroxide. This is what magnesium hydroxide looks like. It's this fluffy, gelatinous, gooey stuff, and it's hard to filter off, and when you filter it off, it retains a lot of that brine in there. If you have too much magnesium in there, you'll lose all your brine in this fluffy goo stuff. And because of that, high magnesium brines are not effective. Bolivia probably has the largest lithium resource in the world, but their salars are very high in magnesium and are not economic. There's one plant going there, sort of, it's on and off. So, so the magnesium can't be too high. Remember, I guess we were talking about, maybe back here we were talking about what's cheaper, brines or pegmatite deposits, spodumene deposits. It depends on impurities. If you have too high of magnesium, you can't make it work because your lithium losses are so large that can't make any money on it. And fortunately, to have a mine, you got to make money. That's just the bottom line. So, okay, so now we're down to here, and at this point now we're going to go get rid of some impurities here, and eventually we're going to precipitate out lithium. We're going to precipitate out the lithium in the end. So the first thing we do here, like I say, we add lime, or in this case the calcium hydroxide, and you precipitate out calcium sulfate, so it removes the sulfate. You also take out the magnesium hydroxide, and that's that gooey stuff. And can't have too much magnesium, or with all this goes all your lithium and it's gone. So the next step they do is they add sodium carbonate, which is washing soda, and you remove the rest of the calcium out as carbonate, magnesium out as carbonate, some more magnesium hydroxide comes out, and you're left with this lithium solution. And the real secret here is, remember how I said that all the alkali metals have very similar properties? Well, lithium carbonate is a little bit different than the sodium, magnesium, rubidium, cesium, in that it has what's called reverse solubility. And what that means, most things when you heat them up, they dissolve more and more, like salt. And sugar is a good example. For sugar, cold water you can dissolve up so much sugar. In hot water, you can dissolve 50% sugar in there or something. Lithium works backwards. In other words, as you get higher temperature, the solubility goes down. And so that's the trick that they use to recover the lithium carbonate, which is the product that's used to make batteries. And so, by doing that, well, let me back up one thing here. By doing this, however, so what they'll do is, say that the brine is maybe about 30, it's probably running about 25, 30 degrees centigrade. So it comes out here at about, say, 12, 13 grams per liter. If I heat this up to 90 degrees centigrade, it's down to maybe, what, 7 or so. So that difference is lithium that I recovered. Well, this solution that's coming out here still got a lot of lithium. That is pumped back earlier into the process. If we look at the process here, you'll see this line coming back here. That's from the crystallization. It comes back here and they recycle that through there. And so, again, they're not going to throw that lithium away, but they can't recover it in the first pass through the process here. And this is what lithium carbonate looks like. Very similar to, it looks like baking soda. I mean, that's a sodium bicarbonate. And they package it up in these big super sacks, and this is how it's sold. lithium carbonate is then used to make lithium metal, which goes into batteries. And so let's say a little over half of this lithium in the world is produced this way. The other half comes from hard rock. So what are improvements that are being looked at, actively being looked at? One is trying to find a way to handle these high magnesium brines. If they find a way to do that economically, that opens up a whole lot more brine resources, particularly in Bolivia. And the other is, the ideal thing would be to find what I call a lithium magnet. If you could find something that would pull lithium out of that brine so you didn't have to do all this other processing, that would be wonderful. Many, many people have looked at this, and we look at a lot at Hazen too. Nothing is really economic to do that. It's just too expensive for one reason or another. Not only would this help brines with high magnesium, but we could process brines that are in non-desert areas. Because remember, you're going to evaporate 99% of the water. Well, you're not going to use electricity or natural gas to do that. It's just way too expensive. So this would open up brines in non-desert areas like these geothermal brines in California. The petroleum production brines, there's some in Alberta that have fairly high lithium content in there. But because you have to evaporate that down to purify it and to recover the lithium, those aren't economic at this point. And although somebody's been trying to process these geothermal brines, and they've been doing it, trying to do that for 15 years, and it's still not commercial. So, okay, let's talk about pegmatites. The primary mineral for recovering lithium is spodumene, and this is spodumene, comes from Arizona. I collected this when I was in high school, and I couldn't believe it actually even found it still. Back in a box, so this is you can see it's a aluminum silicate with lithium in it, and here we can pass this around. You can take a look at it here. And so that's one of the primary, that's the primary mineral that's used. Minor amounts of petalite also is mined, as is lepidolite. Lepidolite is a lithium mica. This is lepidolite that comes from the same place that the spodumene does, comes from Arizona. It's not terribly pink. Usually lepidolite's pinker than this, but this was actually mined for, small amounts were mined for lithium. Probably mostly going into ceramics at that time. So those are the three major minerals, but it's mostly spodumene. We're going to focus on spodumene. Why? So what you have to do to get that rock, which by the way, that rock, you can't dissolve it in hardly anything. And to recover lithium, you got to dissolve that lithium. And so, I mean, you could dissolve it in hydrofluoric acid, but you're not going to do that commercial.
I would think it would be lightweight.
I don't think it's much different than feldspars and stuff. Pete can tell us, because Pete knows everything. Spodumene, it's about the same density as like feldspar and stuff, right? The density of spodumene, it's about like feldspar, right?
I think so.
Yeah, that's what I think too. So I don't think it's abnormally heavy. So
What is that, opal?
okay, so these pegmatite deposits are mined, open pit mines. This is the largest one in the world. It's the Greenbrushes lithium mine in Western Australia. But these are scattered around actually around the world. At one time, spodumene was mined in the United States, I think in North Carolina, I believe. And but again, Australia really has the largest deposits of it, but there are active mines around the world mining primarily spodumene. Okay, so what do you have to do to get lithium out of spodumene? Remember I said that spodumene won't dissolve in much of anything. And however, there's a trick. If you heat this up to about, well, 1,150 degrees, which is about 2,000 Fahrenheit, you convert the crystal form from alpha spodumene to beta spodumene. Beta spodumene will dissolve in acid. And so that is the key to making this work. So the first step here is that to heat this up, it's called calcining, and they use, let's back up. I'm sorry, I jumped ahead of myself a little bit. The first thing you have to do is, when you mine the pegmatite, there's other things besides spodumene in there. And so what you need to do is you need to concentrate the spodumene and reject other things. So pegmatites are full of feldspars, they're full of, there'll be quartz in there, there's other minerals in there. Those minerals are going to also, when you go dissolve the spodumene, it's also going to dissolve those other minerals too. That's going to cost you a huge amount in acid. Now you're no longer economic. And so you got to reject those other minerals. We want to reject the quartz out of there. We want to get the feldspars out of there, some of the other micas out of there that have no lithium in it. So the first thing you do is you take the rock and you crush it and grind it. They use great big they're ball mills. You can see how big this is. There's people right there. So these ball mills are huge. It's probably 15-foot diameter, 12 to 15-foot diameter. And they have, what they have inside of them, they have big steel balls. The biggest ones are probably about as big as my 2 fists here. And they put those in there. They put chunks of rock in there up to maybe 6 inches. And this thing rotates around. It's kind of like a rock tumbler. Only in this case, you got, instead of using grit, you're using steel balls about this big around. And as that rolls around there, it bangs into the rock and it breaks it down into essentially a sand type consistency. So that's what you're shooting for there. And then the next step is to do the separations, is use froth flotation. A flotation cell looks like this. There'll be an impeller here with these blades on the bottom that spins around real fast. They pump air down here, and this thing chops that air up into bubbles. And so that's what it does here. And then the slurry comes in, the feed comes in here. So they slurry up the ground up rock in water, and they go through here. They add special chemicals so that some of the minerals will float, are hydrophobic, they don't like water, and some are hydrophilic, they like water. And so what they do with the lithium is they add certain chemicals, reagents, that make the spodumene so it's hydrophilic, it doesn't like water, and it'll stick on the bubbles. Things that like water will just stay in the slurry and just kind of just float around in there. And so that's really the trick for flotation. It was, it came online about 1900, actually for zinc operations. In Colorado was the first place that it was actually used. But they use that, the flotation plants, they look like this. That's obviously not spodumene, that's a sulfide of some sort, but I couldn't find a good picture with lithium flotation. But this is what they look like. You can see all the bubbles here. It just kind of, what will happen is it bubbles up here, the bubbles come over the top here, and it's captured here, the bubbles break apart, and now you've got the product that you want separated from all this other stuff that just goes out here to a tailing pond. So this just kind of shows how it works, is that you have things that are hydrophobic, that don't like water, hydrophilic, that like water and don't like water. Things that are hydrophobic tend to slide around off these bubbles and fall off, whereas the things that like them hopefully will stick on the bubble, and don't do that. So that's kind of what we're looking at here on a small microscopic scale. Okay, now, so we got through here. Now we're going to go dry this stuff and do the conversion. Those kilns look like this. This looks like a cement kiln. So it's a big, long shaft here. The natural gas fired, so there's a natural gas flame that shoots across here. And they get it up to about 2,000 Fahrenheit. The alpha spodumene is converted to beta spodumene. Now we've got it in a form that we can get the lithium out. So anyway, so we've gone through here, we get it cooled down, we're going to mill it up and grind it up some more. It's kind of like sand consistency here. Here we want it finer than that to be able to dissolve it. And so we add sulfuric acid and mix this thing up under temperature, add water to dissolve the lithium, and then we're going to filter it out. And we'll end up with, the lithium will be in this liquid stream here, and the least spodumene residue goes off and goes off to your tailings pond. Okay, so now the downstream processing, like I say, we've concentrated it, we add sulfuric acid, we add water, we leach it, and then we're going to come off of here and do, again, some steps to purify it. The spodumene has a lot of aluminum in it, and so to get the aluminum out, you cool it, and you'll form alums. What is potassium alum? Which is like the alum that you can buy to make, you're going to make it pickles or something, you buy potassium alum. And it's a potassium aluminum sulfate. Others in that row, that I remember that alkali row, will also form alum. So you get also rubidium out. Rubidium is a product. If there's a high enough rubidium content, they will capture the rubidium. They use rubidium and cesium also in drilling muds because it's very, very dense and very heavy. And so that's a product they can do. They'll add lime, and then iron comes out, aluminum comes out, magnesium comes out as hydroxides. They'll put the soda ash in there and knock out the potassium. And then they'll do the same lithium carbonate crystallization that we showed before. So these are what the plants look like. And again, these are great, mainly just great big tanks, but you can see the size of this tank with the people there. And here's this reverse solubility curve again. So what we're going to do here is come out here and about here, cool it down, take off lithium carbonate, will crystallize out, and we can collect that. The liquid that's left has lithium in it, goes back into the process again, and so that we can cover that lithium. And same kind of product comes out of there. So let's talk about these hectorite clays. These are all the biggest things that are going on right here. This is what's getting all the press now, at least in the Denver Post. And hectorite is a soft, greasy, white clay mineral. And let's say Nevada has large deposits of this, and they contain lithium. Some issues. Clays are very difficult to process. When you take a clay and you mix it with water, it makes these thick slurries, and they're hard to filter. You can't get the liquid away that has all your goodies in it. And also then when you go to dissolve that in acid, because again, we got to get the lithium into a liquid form so we can recover it. All the other clay materials also, acid attacks them also. And so you have huge acid consumptions, which is why those clays have not been made commercially viable at this point. Tesla is developing a non-acid process. And if you look at their patent application, which we're assuming is what they want to use, what they're doing is they're adding sodium chloride salt, it's table salt, and they're using high energy grinding, and grinding it for like 30 to 60 minutes. So it's going to be terribly energy intensive to run these things. But they may not have to use acid. Now whether this can work commercially, I mean their patent says it works, but patents lie. I have 11 patents with my name on them. They don't lie, by the way. They're all good.
They're all good.
But anyway, the patents do lie. So anyway, it's interesting. An interesting idea here, how they may be able to get around with that high acid consumption for these clays. The jadarite I've talked about here too. You can see it has lithium, Li, it also has a boron. So it's kind of attractive in that it has, you can recover both boron and lithium from the same material here. Rio Tinto is working on this. Rio Tinto owns the Bingham copper operation in Utah. It's actually, I think, an Australian company. Or maybe it's British, I think it's a British company. And they're developing this huge deposit that's in Serbia, this mineral. However, the Serbian government and Rio Tinto are fighting among themselves, and Serbia has shut them down at this point. So they're going to have to resolve whatever the problems are to get this operational again. But yeah, I think this one has a lot of promise to it too, particularly with being able to co-produce boron with it too. Okay, now let's talk about batteries. All this lithium is going to batteries, and why do we like lithium for batteries? The two main things we want for batteries: one, they have to be rechargeable, and two is something called energy density. In other words, how much power can you get, energy can you get out of this battery for a given amount of weight? And this is in megajoules per kilogram. Don't worry about that thing, but of course the bigger the number, the better. This is energy per how much it weighs, okay? So if you look at this alkaline batteries, they run 0.3 to almost 0.7 kind of thing, but you can't recharge an alkaline battery. So this higher number is pretty nice here. lead acid battery that well, most of us have in our cars, unless you're driving an electric car. Lead acid batteries have been around for over 100 years. They're terribly dependable. They last a long time. But as you can imagine, because they have lead in them, their energy density stinks. But they are rechargeable, and they're very dependable. Some of the other things that have come out in past that kind of have fallen by the wayside here for rechargeable batteries were the nickel cadmium and the nickel metal hydride batteries. Obviously with cadmium in there, it's a very poisonous metal, so that was one of the real downsides of that. They got around that by using metal hydrides. Energy densities are really bad. If you look at lithium ion batteries, high energy densities and quite rechargeable. Other things you look for in batteries, you have to have a long battery life. In other words, you got to be able to charge it and discharge it and charge it and discharge it over and over and over and over again. You want high power availability. In other words, the nice thing about lead acid batteries, you can get a lot of power out of that real quickly. That's why it turns your starter motor over so nicely. So you need to have high power availability. You want something also that can operate hot and cold. Like for cars, I grew up in the Phoenix area. Well, you got to have batteries that can handle 100. I mean, it can get 120 degrees, and if you're in the sun, it's going to get 150 degrees in your car. Or if you live in Minnesota, you're going to have something that's going to, that'll crank over at like minus 30 or minus 40 maybe. So you got to have a battery that can handle those kind of temperature ranges too. So there's a lot of issues that you've got to be able to solve in making a battery that's commercially viable. So here's how batteries work. This is a lithium battery, but all batteries work kind of the same way. Now we're going to get some more chemistry because I love chemistry. And so you have anode and a cathode. The anode is the negative side of your battery, and the cathode is the positive side. And what will happen is chemical reactions take place in here, in which case, at the minus, it produces electrons, which are negative. And when you connect the switch here and flow through any kind of power source, this has a light bulb, but this could be your car, if you have a Tesla. This could be my cell phone, whatever's going to needs the electricity here. When you shut that, the electricity flows from here over to the plus side, because these are minus and these are plus, and they're attracted to each other. And then you have, when current flows there, that's when you get the power out of a battery. Okay, so that's what you got to have, and you have to have magic chemistry that goes on inside here to make that work. And for lithium, here I told you we're going to do chemistry. Here's what's happening here. On the anode here, you have actually graphite. Graphite forms sheets, and in between those sheets is the lithium metal. So, that one video showed where he's pulling out this big thing of lithium. Most modern lithium batteries now just have layers of graphite with the metal in between there. So you probably can't pull out big sheets. So don't go try that anyway. Besides that liquid, that black liquid that dripped out of there, that's really nasty. You don't want to get that on your hands either also. So anyway, so the lithium metal is in between the graphite here. And so you'll have approximately, they make it up so that there's like 6 atoms of carbon in the graphite for every atom of lithium. And what happens is the lithium forms what's called lithium ion, which dissolves in that liquid and produces electricity. The electrons here. On the other side, there's a number of different types of oxides that they use here. All of them have cobalt, which is why cobalt is another one of these really critical metals that's causing a lot of concern right now for availability. So what happens here is, in this case, the cobalt oxide and lithium form together along with electron to form this compound here. They also have some that have magnesium oxides in them. There's a lot of other different kind of cathode materials that they're looking at, but really cobalt's really critical for this at this point. So that's what's going on there in the battery. So okay, so first thing is how do you keep these things from bursting into flames, particularly when you carry them around your pockets, right? Okay, lithium is highly, as you saw, is highly reactive. It burns in air, and it really explodes in water. And so if you get a lithium battery, the inside of it wet with water, it's going to blow up. In fact, an earlier cell phone I had actually started warping. And at that point, I said, carrying that in my pocket anymore because I know what lithium is. And also that electrolyte that's in there, you can't use water inside it. I mean, a car battery has water in it. An alkaline battery has water in it. Can't have water in there with lithium because it'll blow up. So it has an organic material in there. It's also flammable. So not only is the lithium going to catch on fire, but it's going to burn the electrolyte up too. So what you need to do with lithium batteries, what's important is to prevent overheating, and also, of course, we don't want a fire. So batteries are designed to dissipate heat. That's why the battery in your phone is nice, long, and skinny. Yeah, it fits nice in a nice, skinny phone, but also you have a lot of surface area so it can keep that battery cool. And the batteries in a Tesla, for instance, they're big packs there, but inside are just layer after layer after layer of that, so you have lots of surface area, you can keep them cool. Another thing that causes overheating is what can happen in there is something called short circuiting, and what will happen is the metals, the solids in there will grow together and kind of grow crystals through there and actually touch each other. And once that shorts out, then you have a huge surge there that heats your battery up. So they've had to design these things so you don't have that short circuiting is what it's called. Also the shell is designed to prevent breaking and puncturing. They've actually figured out if you take the battery, say, out of your phone and drive a nail through it, it will not blow up here because they have now engineered those things so that even puncturing it, it'll self-seal and it won't catch on fire. So by engineering design here, they've made these batteries that prevent this sort of thing from going on, unless you really abuse your phone. Okay, so what happens? What are future things? Obviously, faster charging times. I think to fully charge a Tesla takes, what, an hour and a half? Well, if I'm driving cross country and I go for, say, 300 miles, and then I got to go to a charging station and sit around and drink coffee for an hour and a half, I'm not real excited about that. So, how do we charge it faster? That's being worked on that. How do we get longer battery life? We were talking here before the meeting here. I don't know what it costs to replace the batteries in a Tesla, but I'm going to guess it's 20,000 or more. And so we want to get as long a battery life as we can here. How do you get them to work better in the cold? And how do you keep them from overheating when it's too hot? Those are things we look at. How can we make them cheaper? How can we make them lighter? How can we make them more powerful? And how can we get rid of that cobalt? Because the cobalt is expensive, and almost all the cobalt in the world comes from Africa. China pretty much controls all those cobalt mines now. So there's a real concern there. Also, they're looking at, well, can you use something cheaper than lithium? And I was just reading the paper just yesterday, I think, they were talking about, well, they're looking at sodium, because sodium is just right underneath lithium. It has similar properties. It's heavier, but it might work there. I said that liquid in the inside the battery, it's called electrolyte, can use a solid instead of having a liquid in there. Again, that would make the battery more stable, maybe make it do some other things too. And again, just to improve general safety. All right, so what's the future of lithium? This is one thing that came out in 2021. As I say, we're at here, so about 100. We're using this scale here. These are 1,000 metric tons, so we're about 100,000 metric tons here. So projections are, you can see where the projections are. This is current production, probable production, and then maybe some maybe production here. But you can see the gap that goes on here. Just 2 days ago, the EPA proposed that emission limits, that's going to require 2/3 of all vehicles sold in the United States to be electric by 2032. Okay, that's probably going to push this up higher than it's already on here. California, last year, California and New York mandated all vehicles sold in those states by 2035 have to be electric. And then last month here, Fernandez, who's the Undersecretary in the State Department, they are now estimating that by 2050, we're going to need 42 times the lithium that we're making now. And so where's all that lithium going to come from? That's a really good question. So, question, okay, so here's how you make lithium batteries, and questions. Yes?
Is there economically feasible to recycle these batteries?
I asked if it was economically feasible. Absolutely, and that's being, I think there's already operations going now. And if you go back to, you go back to this thing, this secondary supply here, that's actually recycling lithium, and that's what that is there. So
If they don't do that, they're just going to be throwing more junk in the landfill.
that's right. Plus, we want the cobalt out of it too, because and maybe even the magnesium, the manganese that's in there too. So yes, recycling batteries, it's already started. That'll just get bigger and bigger. They won't throw those batteries away. Back there.
No, that was the same, about recycle.
Other questions?
I
Yeah, go ahead.
have kind of two questions.
Okay.
One is, what do they use the cobalt for?
So the first question is, what do they use the cobalt for? The cobalt is important in the chemistry. Let's back up a little bit. The cobalt actually combines with the lithium, so that's the chemical reaction that has to take place over here for the battery to operate. Okay?
Second question, I'm not sure if you can answer or not. After they process the lithium and they have it in the bags to be sold, like how big are those bags? Like what do they sell for? If you can answer those, I don't know.
How much is in those bags? Those super sacks probably have, I'm going to guess, they probably have a ton or so of lithium carbonate in there. Now lithium carbonate, because lithium is so light, probably only about 7% or so of lithium carbonate is actually lithium itself. The rest is the carbonate part of it. So, and what does it sell for? The last prices I saw, it's come down a little bit right now. I think the last I saw it was selling for $7,000 a metric ton, I think. But that's about 5 times. It's selling for about 5 times what the production costs are right now. So that's going to come down here. That can't be sustained. So, and don't quote me on that price too. I may have that way off. So
I think she asked, what do they use it for?
No. He answered it.
Yes.
okay. And that price, I may not have the right units on that. I know it's 7,000, but I'm not 100% sure on that one. So, any other questions? Yeah.
I'm curious what lithium deposits we have here in Colorado. I'm assuming they'd all be pegmatites, and are they large enough to consider for mining at all?
Certainly would be pegmatites. I know Pete.
Brown Derby mine.
Pete, are there any lithium mineral pegmatites in Colorado?
Brown Derby mine.
Are there any?
The Brown Derby mine by Gunnison has a lot of lepidolite.
Okay.
And there are some in Larimer County in the Crystal Mountain District that have spodumene.
Okay.
But there's not enough to be mining it the way things are now.
Okay, thank you. So, yes.
I haven't heard, would you happen to know, are they still trying to develop the hydrogen fuel cell as a power source for a car?
You know, that really hasn't been making a lot of press. I'm sure there's still work going. Oh, he asked about hydrogen fuel cells. That still is being looked at, yes. It doesn't seem to be getting all the news right now. It's not nearly as far along commercially, of course, as the lithium batteries. But that very well may be a source in the future. One of the issues with generating hydrogen is it takes natural gas, because that's where the hydrogen comes from. You react natural gas and water together, and so you produce hydrogen. But also in that reaction, you produce carbon dioxide, so you have to capture that carbon dioxide too. So I guess the bottom line is there's no such thing as a free lunch. This is the bottom line. So, other questions? Yeah.
All right, I don't know how quite to phrase this, but is there a way to predict how much lithium might be available on Earth in any form? And if there is, and we were able to figure out how to extract it in an economical way, would that meet the needs over the next few decades?
I'm I'm gonna guess now, okay? I don't know the answer. My guess is yes, there's probably enough lithium to do that. Certainly what'll happen is the price will go up and make some of these marginal deposits economically viable. And so I think it's there, but you need to kind of think about, to get a mine operational, in the best of situations, could take 10 years. And so, and there are a number of mines that are, lithium mines that are now in various stages to commercialization, but that lag time there is really going to be really critical in producing that much lithium. And really, in my mind, what will happen is we'll get another source of another battery source. Maybe it'll be a hydrogen cell, fuel cells like you're talking about. That may be one of the options too down the road. So I think it's going to be a combination. We've got to ramp up lithium, but we also got to find other sources of energy to run like the cars. So, yeah.
I'm still trying to get my mind around the fact that lithium explodes in water, but yet water is where we're getting lithium.
Well, it's not, in water, it's not as lithium metal. It is as lithium ion. And so, so it is a metal that explodes in water, but when we're recovering lithium, we have it's in the brines as lithium chloride. It's like sodium. Sodium metal reacts very much like lithium. If you throw sodium metal in water, it'll catch on fire and might even explode. But we can combine that with chlorine, which is a highly toxic gas used in World War I to gas soldiers. We combine sodium metal and chlorine gas, and we make salt, sodium chloride. And so lithium's the same way. The lithium that we have in like the brines is lithium chloride. So it's like salt water. And so it depends on the form of the lithium. It's maybe the best way to think about that. Anything else? Okay, well, thank you, everybody. Thank
you. Jerry, I'll add something else. When you talked about spodumene, which is one of the main lithium minerals that occurs in pegmatites and is mined for that, and you passed around a piece of it, but you didn't make any reference to the fact that when spodumene is transparent, it's a very popular and valuable gem mineral, which of course everyone knows what that is that we're talking about, right?
I know what it is.
Except for the new company.
But I don't think you want to grind that up and make lithium metal out of that stuff.
Yeah, I was going to say,
which is
Kunzite.
called kunzite when it's pink and hiddenite when it's green.
You can grind that up and run it through those plants if you like, but I don't think you want to.
well, thank you so much, Dennis. We really appreciate that. I know I enjoyed the show. Very interesting. All right. Did anyone else have anything else to bring up to the membership? All righty. So it is raining outside, so I want everyone to drive very carefully on your way home, especially if you're driving an electric car in the rain. Just saying. All right. Thank you all for coming once again. Have a lovely evening. And there's still some food over here, so feel free to grab something on your way out.